Welcome to Math 106, Chapter 4.5, where we talk about derivatives of natural logs and logarithms. So we talked about the other day how the relationship between E and ln work, that they are inverses of one another, and that really helps us form that relationship. It makes our lives a lot easier. We also talked about the chain rule and how to apply that to your derivative. So what I want you guys to do for this warm up is to take the derivatives of both sides. Now you will not know how to derive ln of x yet. We're going to learn how that comes up and is created. So we're deriving that, if you so to speak. So when you'd use your chain rule, when it comes to the chain of this, just leave it alone. Just use your symbolic meaning for derivative. So first, right, derivative of this side, right, is just 1. Now, when it comes to your other side, your derivative, right, well, we know that the derivative, d over dx of e, we'll say to the g of x, is just the derivative of e, leaving g of x alone, times the derivative of g of x, right? So for us in that format, when we go to derive, right, we get to derive e, which is just itself, leaving behind or just keeping your ln of x alone. And now we are asked to derive your ln of x. Well, we don't know that yet. We're going to come up with some sort of a response here. So we're just going to leave that alone. Now let's hone in on the relationship between your e and ln of x. Well, e with an ln of x has a base of e, and as we learned from our last class, is that they will cancel one another out and allow your x to just drop, or your exponent, whatever it is, it'll drop. Therefore, you have x times the derivative of ln of x, whatever that may be, is equal to 1. So if we're interested at the end of the day to figure out the derivative of ln of x, well, what's going to happen? Well, we're going to solve for that. So we can go ahead and divide both sides by x. So we have the derivative of ln of x is equal to 1 over x. This is your proof. This is how you derive ln of x. So ln of x, the derivative of that is just 1 over x for when x is greater than 0. We have to keep in mind it has to be greater than 0 because you cannot have x being at 0, especially now that it's in the denominator. And on top of that, right, when we looked at your graph about ln, we said there are no negative x values. So we now have to keep in mind that that would just mean that x is greater than 0. So you'll see that here. So this is your relationship, why we hone in that skill of just kind of canceling out those properties, right? Because they share that relationship. Now, when it comes to the logarithm, the derivative of your log, right? We'll just say this is just the derivative of log base a of x. We'll just say, okay, we're using that same relationship of 1 over x. Now your log is still, it has that relationship of an ln, like that is totally fine. So we have ln of a. So your a, we'll say that, is your degree here, not degree, your base. So we'll put your base on the inside. And because of that kind of chain rule, or that chain rule aspect of it, right? We're going to be dividing by your x, leaving behind your derivative of your log. Let me see, is there anything else I want to emphasize? One more. So this is the derivative of a log. We now have the derivative of ln itself. And now let's take a look at the derivative of anything that maybe is something like b to the x. So previously, when we first saw this, we said, hey, this is really just m to the bx. Now we're going to hone in and come up with now a more basic form of your derivative, now that we know the relationship between x, or relationship between e and ln of x. So if we have something that we have b of x, right? we could also write it in a kind of roundabout way to say e to the ln of bx, or what we know about your properties is we push this x to the outside. So we have e to the x ln of b. Now we know that the relationship between e and x, this will cancel and allow it to drop. So this is kind of just written out longhand. Now, when it comes to your derivative, right, using that chain rule aspect, if we have the chain rule of this, right, if we're asked to derive e to the x ln of b, that would just be this thing right here, is that with that chain rule, well, derivative of e is just itself, leaving everything alone. And now multiplied to the derivative of x ln of b, right? ln of b, that is going to be some sort of numerical value. And you'll notice that x here is just x. So this will become 1 times your value. So it'll leave behind ln of b. Now, what's nice about this form, and I'm just going to push this form up a little bit to give myself a little bit more room, is that the derivative, not the derivative, but the simplification, where am I? Sorry, I moved up. The simplified form, as we talked about here, right? E to the x ln of b, if we throw that back up on here, is that these will end up canceling in b of x drops. So this part becomes b to the x times ln of b. So that's how you can get any sort of derivative for an exponential that is not written in the form of e. We use now what we know about the relationship between e and ln, as well as the aspect now that we understand the chain rule. So there are a couple different things. Let me just put a box around these maybe. So this is one additional rule. And this is another additional rule. There you go. And of course, your third rule here. So we just learned 3 separate rules, kind of using that relationship between E and ln. So now let's compute your second derivative. So if we say d over dx, right, of ln of x, we know that your first derivative is equal to 1 over x. So your second derivative of x, if we raise it up to the first power and we said, okay, d over dx, right? That -1 comes down. We have now x. Subtract 1 more, so we're now at -2. So you'll notice that your second derivative doesn't follow the natural log. We don't have to write it, right? Instead, it's just going to take over exactly as normal. And then you can take the third and fourth derivative and so forth. Now, let's say I posed a question that said, how is it that the first derivative is positive while your second derivative is negative? Now, keep in mind your first derivative tells us information about what? Your first derivative is all about your slope. So if your first derivative is positive, right, your slope is doing what? Well, your slope is positive. It just means that it's increasing. Not so much increasing, but like it's going upwards, right? Positive, going up. Whereas your second derivative, right, this is what information does it provide us with? I'm going to actually push this to the center. Your second derivative tells us about your concavity. So if your second derivative is negative, well, what does that mean about your concavity? Well, that would mean that it's concave down. So it should be concave down while all of your tangent lines are still positive, right? All shaped upwards. So if we take the graph of your ln, look at all of your tangent lines, right? Well, your tangent lines, they're all positive. Yes, they are slowing down, right? But no matter what, they all are positive. Whereas your second derivative, right? These are all downward facing. So these are all concave down. That's why we have all of these as being negative. Concave down, slope positive. So that's why we have that change kind of in your signs between your first and second derivative. So now let's have you practice differentiating your following. So let's take a look here, right? Well, you'll notice that x is not only trapped in your ln, but it's also trapped within your degree. So the first thing we need to do is to bring your 5 all the way down, right? Use that chain rule. So we have 5 ln of x now to the 4th power. This is the derivative of y. So now that we took care of that, we can go ahead and derive ln. The derivative of ln we just learned is 1 over x. So we'll multiply by 1 over x. So therefore, when we put it all together, right, we have x that's down below from your derivative. And we have 5 ln of x to the 4th. Let's try it again. So over here, we have x, ln of x. So we have the product rule. F of x, we're going to say is just x. The derivative of it is 1. G of x is ln of x. G prime of x is 1 over x. So when we put it together with your product rule, we said we kind of just take turns deriving. So the derivative of your first is just 1 times ln of x plus x times x. So we're left with ln of x plus, and these will end up canceling, so plus 1. I'm going to have you do just a couple more. Let's do 39. So f of x is equal to e to the x. F prime of x is itself. G of x is ln of x. G prime of x is equal to 1 over x. So putting it all together, right, we have e to the x times ln of x plus e to the x times 1 over x. So let's see if we can take out some things. So we have e to the x, we have ln of x plus 1 over x. I'm going to see if there's another one. Let's do 45. So here we have your chain rule, right? Your x is on the inside of ln. So first thing we need to do is the chain rule. Chain rule says derive the outside function, keep the inside the same. So our derivative of ln, we know to be 1 over x, but our x is now this whole thing. This is g of x. So we have 1 plus e to the 2x. Now we need to multiply by the derivative of g of x. That is times e to the 2x times 2, another little chain rule segment. So we have 2, e to the 2x, all over 1 plus e to the 2x. And I'll see, do we have a couple more? Let's do just one more, maybe two more. Let's try out 39 and 41 and 49. So just three more. Now keep in mind what we talked about with your derivative here of your exponential. Keep in mind it's an exponential without your e. So with that, right, we said if we have b to the x, or the derivative of b to the x, this is just b to the x times ln of b. So this is your b, right? Or I should say base is 5. This is acting as your base, and this is acting as your x. So when we go to take your we would say, we'll say ln of b, so that would be ln of 5 times 5 to the negative 4x. And now we need to take the chain rule, which is negative 4. So all in all, we have negative 4 ln of 5 times 5 to the negative 4x. Let's try it again with the one down below. So we'll say f of x is x. So that's 1. G of x is equal to 9 to the x. So this is acting as your b here. So the derivative is equal to ln of b, so that would be 9, times 9 to the x times your derivative of x, which in our case is just 1. So we have 9 to the x times ln of 9. So for us to put it back together, we have 1 times 9 to the x plus x times 9 to the x ln of 9. Now you notice that you have two 9 to the x's, so we'll take that out. 1 plus x ln of 9. One more. So keep in mind your logarithm has your own derivative. That is 1 over, well, actually, let me write it out better. So if we have d over dx is log a, actually, I want to write log b because that's kind of signifying your base of x, right? We said this is 1 over x ln of b. So for us, this is your b here. This is your base. So we also need the chain rule of the inside if needed, right? But we have 1 over, your x is from the inside, so that's 1 over 4 minus t squared. So that is just x times ln of b, that would be 5, times your chain rule here of 2, 4 minus t times negative 1. So here we should have negative 2, 4 minus t over 4 minus t squared, ln of 5. We can get rid of one of those, negative 2 over 4 minus t, ln of 5. And that chain rule, you can see right here as well. The derivative of the top, that was from here. We have ln of a, that is acting as your base here. And then u is just being placed right next to it here. So if you wanted to do it again with maybe 48, you can. I'm going to show your answer key over here. All right, so let's go back to your guided notes over here. So let's take a look at the chain rule with your ln, which we did a small portion of it before we did our quick little worksheet. But keep in mind with your derivative of ln, right? Take the derivative of your outside function. So the derivative of ln is 1 over x. However, it comprises of g of x, so we keep g of x the same, and now we derive g of x. So the derivative altogether, as you kind of saw from that worksheet, they kind of showed you, hey, what goes up and what goes down. For us, the derivative of g stays up typically, and the underived portion goes down. That is because we had ln on the bottom. And again, you can do it when you have your actual composite function together. So let's see if you can try out example 2. So here, right, we have f of x is equal to ln of x. And you also have your g of x here is equal to 2x plus 1, right? If you get rid of this 2x plus 1, that's your inside function. You're just left over with ln. So now when we go to derive, right, ln is just 1 over x. G prime of x is just 2. And so your chain rule just says, hey, let's take f prime of x times, f prime of g of x times g prime of x, which will come out to say we have g prime on top over g on bottom. So for us, right, putting it all together, we have your f prime here. We have 1 over, and instead of saying x, we're going to take g, which is 2x plus 1, times the derivative of g, that is 2. And when you clean it up, you should get 2 over 2x plus 1. 2 over the 2x plus 1. Let's try it again here. So here we have f of x one more time is ln of x, and its derivative 1 over x. G of x is everything on the inside. 8x minus 2. So for here, let's put it all together. If you want and already can kind of see where it's going, right? 1 over, so this up top and this on the bottom, that is perfectly fine. So we have 1 over 4x squared minus 2x plus 9 times 8x minus 2. So you have 8x minus 2 over 4x squared minus 2x plus 9. So looking at the numerator, we can take out a 2. So we have 4x minus 1. And the last part is not factorable. So we'll just leave it as such. And the last one, C. So again, you're going to have to do the chain rule here along with the product rule. So chain first and then product. So chain rule, right, in order to derive your x values, chain rule, we now need to do 1 over x e to the x times the derivative of the inside So that's when we can use your product rule, right? We have x, which is just 1, e to the x, and this is all being multiplied, plus x, and then the derivative of e to the x is just itself. So when we put it together, right, we have e to the x plus x, e to the x, over e to the x. Well, what do they all have in common? Well, they all have an e to the x in common. If you wanted to factor it out, we could factor out e to the x, leaving behind 1 plus x. Over x e to the x. But you'll notice that we can cancel, and you're left with 1 plus x over x. And no, those x's do not cancel. All right, I believe we have our last one, which is example 3. So the function f of x is equal to ln of x over x has a relative extreme point for some x is greater than 0. Find the point and determine whether it has a relative max or min. So we now know how to derive ln. We now know how to use your quotient rule, and we also know how to find a relative extrema with either a max or a min. So this is all coming together. So chapter 1, 2, 3, and now 4. Let's see what you can make of it. Well, step number 1, we have to derive. So f of x, we have ln of x, which we now know your derivative is 1 over x. G of x is just x. G prime of x is just 1. So we now are using your quotient rule. Your quotient rule, right? Because two things are being divided. We have 1 over x times x minus ln of x times 1 over g squared. And you'll notice that these two will cancel and just leave behind 1. So you have 1 minus ln of x over x squared. So now, step 2 is to determine critical value, because this is f prime of x. We know for critical value that your derivative has to be equal to 0, right? Your slope is equal to 0. You have a horizontal. So if we know that we have 0 on one side is equal to 1 minus ln of x over x squared. We have an x squared on the bottom. So right away, let's go ahead and multiply both sides by x squared. That'll allow us to cancel on one side. So we're left with 0 is equal to 1 minus ln of x. So we're solving for ln of x. So let's go ahead and subtract the 1 to the other side. We have a double negative on either side, so those can cancel. So we have 1 is equal to ln of x. So x right now is inside your ln, right? So how do we solve inside ln? Well, we get to use either your swoop method or your properties of inverse, which if we have ln that has a base of e, we can take e of both sides. That'll allow me to cancel on this side and x will drop. So we have e to the 1 is equal to x. So that just means that your critical value is e. And now we need to figure out, okay, well, what is the point, right? Because I think it just says it has some, oh, we just want to determine if it's a max or a min. So we don't even need to figure out if it's a full on point. If we want to, we certainly can. But this is when we can use your second or first derivative test. So step number 3, either the first derivative test or second derivative test when x is equal to e. So it doesn't matter which one you choose. You might want to choose the first one just because your derivative, your first derivative has a quotient rule again to it. So it depends on how comfortable you feel with the quotient rule with some of our new stuff. Otherwise, the first derivative test, keep in mind, e is approximately 2.72. So you can type in maybe a 0, a 1, kind of any sort of number into your first derivative. Keep in mind your first derivative is 1 over ln of x over x squared. So keep in mind, you cannot choose 0 because you have 0 down here. However, you can choose a 1. And what relationship does ln of 1 share? right? Well, that just means we have 0, right? E to the 0 is equal to 1. So 1 might be the best aspect to choose, because if we have the derivative of 1 minus 0 over 1 squared, it's just 1, which is positive. So we know that your slope is going up. Here it's horizontal, right? Your slope is equal to 0. This one is positive. And then we can choose any sort of number on the other side. So you could choose 3, you could choose 4, but keep in mind what we're looking for, whether it's positive or negative. So the first derivative, when it's equal to 3, is 1 minus ln of 3 over, let's see, 3 squared. So that is 1 minus ln of 3 over 9. Now we need to determine, okay, is ln of 3 greater than or less than 1? Well, we know that, I think we said it the other day where we said ln of, what was it? Oh, I think we just talked about it. ln of 4 was about 1.4 or so. So ln of 3 should be a little bit bigger than 1, but let's go ahead and confirm. So we have ln, and we said of 3, so that's 1.09. So it is going to result in a negative number. So we know that this is going down, so it's negative. Therefore, do we have a max or a min? Well, we went positive, we bottomed out, and then we went down. So we have a max here. Otherwise, you can always take your second derivative here from here and then choose to put in E if you wish to determine, do you have a concave up or down graph?